Good afternoon, everyone. I'll be speaking in English. I hope this is okay. You wouldn't want to hear my French, it's not very good. So, yes, my name is Antonia. I'm a master's student from the University of Bologna, being supervised by Loic Bertrand at the ENS Paris-Saclay. And I'm here for 6 months to work on a thesis. And the thesis topic is the study of varnishes using photoluminescence imaging and digital methods in the context of paint conservation. Okay, so a quick side note before I begin is that I started this project last month in April, so it's a little bit basic at the moment, preliminary steps, so any questions at the end, please go easy, and I will try to answer the best that I can, but yes, okay. So to begin, I will talk about the background of the project. Maybe some of you have heard about the larger European project, Go Green, which is aiming to improve, well, green conservation. And so as part of this, the team from the University of Bologna has been working on greener solutions for the removal of painting varnish. And the scheme on the left shows one of their solutions, which is the application of an electrospun fiber or tissue impregnated with a greener solvent. This is applied to the surface of a painting, applied to the varnish in order to swell, and then it is removed. And this method has been applied to a simple system so far with Damar varnish. And already we know that this system, compared to common painting varnish removal techniques, is quite non-invasive. It's user-friendly and safe for the user, greener than the common solvents used in painting varnish removal. However, we need to understand how effective these new treatments are in terms of their removal of varnish and potential for leaving residue on the surface of paintings. So one of the ways that we can assess the efficacy of varnish removal in paintings is through the exploitation of the ability of some varnishes to luminesce. So as you can see on the left, we have a painting in oil, and on the right, when illuminated with ultraviolet light, we can see that this whiteness appears, and this whiteness is arising from the luminescence properties of the varnish applied. So some varnishes, in particular, some resins from trees, for example, Damar and mastic, have the property to be able to absorb light at certain wavelengths, energy ranges. They can absorb this light. There is some sort of energy loss within here, and then energy can be emitted at a longer wavelength by a fluorescence or phosphorescence, and together we can describe this as the property of luminescence. So the system in question that we have been testing the cleaning, I will go into in a bit more detail. So it's a multi-layered system. We begin with a support of wood. On top, we have a ground layer of gypsum and rabbit skin glue. Above, we have a paint layer consisting of, again, rabbit skin glue as a binder and burnt sienna, a mineral-based pigment. On top, we have the application of Damar varnish, which is a triterpenic resin. And then we also have the potential for exogenous materials to appear before or after cleaning, for example, dust, fiber, or dirt. And in bold are the materials which have the potential for luminescence. So the varnish will luminesce quite strongly, as we can see in the cross-section illuminated with ultraviolet light. We have the varnish, the support due to the proteinaceous glue exhibiting luminescence, potentially a bit of the paint layer, as well as these exogenous materials luminescing. So the luminescence imaging, I'm going to describe the setup that we are using at Ipanema, one of the laboratories of the synchrotron. And in particular, this setup is a custom setup by Mathieu Thury. I'll stand this way. So what we have is our paint sample here. It's black because it's dark in this room. We have excitation of light. We have a choice of 16 wavelengths. For example, purple being in UV. This light goes through to a fiber optic ring, which then comes down and illuminates the surface of the sample in a cone shape. The sample, for example, the top layer of the sample being damar varnish, can absorb this light, this UV light. There's luminescence. The luminescence is emitted. This here is a choice of an emission filter, which is a choice of wavelength of which we want to filter the emission in order to capture it as an image by our camera. So here we have the choice of 16 excitation wavelengths, and we have 8 emission, I guess, wavelengths, so they are a range of wavelengths to capture. And here we have the cleaned sample, the one that I described before, in our setup. And through this imaging, photoluminescence macro imaging, we are able to get an idea of the nature of residues of the on the painting. For example, if they are varnish or if they are exogenous materials. We can compare areas of varnish thickness. And this allows us to evaluate the efficacy of the treatment developed at the University of Bologna, which was the tissue with the solvent. So some work done by a PhD student in my group is the analysis of these photoluminescence images of this system and the use of mathematical exploratory data analysis to be able to link thickness of varnish with optical response. So here we have quite a complex plot, but we have the excitation wavelengths here. These groups are the emission filters. And through the use of k-means, here we have an image of a cleaned spot where the center yellow portion is, we assume, to be completely cleaned, no varnish remaining, and the purple is our complete varnish layer. But we see, interestingly, that there is a gradient between yellow to purple, and this is where we think, okay, maybe we can use photoluminescence imaging and the intensity of luminescence in order to understand how much varnish is remaining on the surface. So I'm going to add here that there are some additional optical effects happening in this environment, aside from purely luminescence being able to be detected by the camera. So in the system, we need to consider the depth of the luminescent layer. We also have absorption and scattering of light within this layer, and we have reflectance between the background, which we consider the paint layer to be opaque, and reflectance also between the air and the varnish layer. And this additional complexities, we have been in discussion with Lionel Simoneau from the Institute P'. So in order to unpack and be able to link varnish thickness with intensity and photoluminescence, we are beginning to design simplistic paint samples, which are just consisting of a luminescent varnish, so damar mastic, commonly used in painting, on a glass substrate, which is non-luminescent. And so we plan to produce multiple samples with different thicknesses of varnish. And the application method for this varnish is quite important here because this is what controls the thickness of... Sorry about that. Okay. This is what controls the thickness of the film, but we also need to consider the homogeneity because we want this layer to be as homogeneous as possible. So we have a few options. We have a spin coater machine at the ENS, which is quite a high-level material science approach, which is under vacuum, the varnish is applied, and through spinning or rotation, we can control the thickness by the rotational speed. We also have quite a simple film applicator that is just done by hand on glass. And we are also considering analyzing the results of common varnish methods used by conservators, for example, just by brush or by airspray. To characterize these samples, we will, of course, use macro photoluminescence imaging, as well as spectrophlorimetry. And then to confirm the thickness of the varnish, we can use profilometry. And all of this will be combined with numerical approaches from some mathematicians at the ENS in order to optimize eventually the parameters for the microphotoluminescent imaging. So moving on to increase the complexity of our fake paintings from pure varnish, we then go towards a simple painting system composed of a wood support with a gypsum and glue ground, a paint layer consisting of a single pigment in a binder, either oil, glue, or tempera, and then the application of a varnish, so probably damo varnish again. This scheme, we have multiple stages of drying, and potentially we will do some artificial aging after the application of varnish, because we know that varnish luminescence in particular changes a lot after aging in terms of increasing intensity of luminescence, but also there is sometimes a slight shift in the maximum intensity in terms of the wavelength. So we aim to produce single pigment samples and then eventually increasing the complexity to include multiple pigments. And for these samples, I'll be working with the painting conservation student, Clara Nabe, who is here today. And so we have designed this system to control for the luminescence response. So here I have a simplistic table of the materials. We have Dama varnish, which luminesces in the UV and blue. We have multiple binders, proteinaceous and oleic in particular, luminescing in the yellow range. And then a range of pigments, which we have chosen based on their quite intense luminescence potential. Zinc white, the cadmiums are inorganic semiconductor pigments, so they have a very strong luminescent response. And carmine is an organic dye which luminesces around the red area. Our control pigment, which does not luminesce, is, as we mentioned before, burnt sienna, which is an earth pigment composed of iron and manganese oxides. Our painting samples we will characterize again with microphotoluminescence imaging combined with microphotoluminescence imaging. And for this, we need to take micro samples, so little fragments of the paint. These are embedded in resin and then studied in a similar setup to the macro approach, although here we are able to see the luminescence response of each layer in turn. We were also able to do spectrophlorimetry on the all of the reference materials alone and in combination to able to understand the fluorescent response of their interaction outside of our painting samples. And again, we are combining all of these results with the knowledge of the mathematicians at the Centre Borelli. So the next steps for my project over the next 4 or 5 months will be to continue with the quantitative assessment of varnish thickness using photoluminescence imaging. We will study the impact of the painting materials of our test system on the luminescence of the varnish, the response of the varnish. And eventually, this is moving towards a collaboration that we have with the University of Amsterdam. The researchers in Go Green, where we are working on optimizing parameters for imaging to improve the ease of use for conservators using this imaging technique to make it more simple and lower tech than the current setup that I showed that was at the Ipanema laboratory. So the last thing I'll talk about is just this image, which my colleague Laura Casals has been working on. So what we have is, on the right is a normal image of a cleaned varnish area of the sample from University of Bologna. And on the left is a false color RGB image of three excitation emission couples from our imaging. So she has chosen optimized excitation emission couples in order to best represent and differentiate the types of residues present on the surface. So the black area we assume to be no varnish, nothing is luminescing. On the outside appearing in green, this is varnish, but we can also see, interestingly, that we have a few what looked like to be fibers appearing in red. And so this is something that we would like to work towards, optimizing the choices of excitation emission in order to being able to quickly and simply assess how well the varnish cleaning is going using these new methods. So with that, I would like to thank all of our collaborators, in particular my supervisor, Loic Bertrand, and Laura Casals from the PPSM laboratory at the ENS Paris-Saclay. So thank you for your attention.